Gross leak testing of high reliability devices in a production environment. Presented by Webb Technology. Part 1, Theory and Background. Gross leak testing is a critical part in screening high reliability devices. Moisture from the air can penetrate into the cavity of a device through leak paths created by cracks and faulty seals. Once inside the cavity, the moisture can corrode the die surface or die pads and cause the device to fail in the field. Thus, it is very important to reject packages with these leak paths prior to shipment. Inferior devices are often called leakers, and without proper hermeticity screening, a leaker can pass all visual and electrical tests even though it could eventually fail. Everything leaks at some rate. Mill standard product is considered hermetic if the leak rate is small enough to assure that the internal package atmosphere can be maintained at an acceptable humidity level for the desired service life of the device. Hermeticity testing is divided by two categories: fine leaks and gross leaks. Fine leaks, those smaller than approximately 10 to the -5 atmospheric cc's per second, have leaks so small that they must be detected by the use of krypton or helium gases. Gross leaks, those larger than approximately 10 to the -5 atmospheric cc's per second, are detected by using liquids. As this chart illustrates, neither a gas test nor a liquid test by itself is adequate to cover the entire leak range as specified by mill standards. A gross leaker cannot be detected through the full range with a gas because the tracer gas escapes through the large leak path too quickly to be measured in a fine leak tester. Conversely, a liquid cannot be used to detect most fine leaks because liquid molecules are too large to penetrate through fine leak paths. In today's mill standard production environment, the two most commonly used gross leak testing methods are the two-fluid bubble test and the NID vapor detection technique. To ensure reliable leak detection in the full leak test range, the two-fluid bubble test employs a preconditioning phase which was not part of the old single-fluid test method. With the two-fluid bubble test, the devices are first preconditioned in a bombing chamber, where they are pressurized with a low boiling point fluorocarbon fluid. This procedure forces the fluorocarbon into the cavities of defective packages through any leak paths which may be present. The two-fluid bubble test covers a wider test range than the old single-fluid bubble test. This is due to the preconditioning cycle, which improves the sensitivity of the testing process, and thus the quality of outgoing product. After preconditioning and a short drying period, the test parts are placed into a bath of indicator fluorocarbon, heated to 125 degrees centigrade. The boiling point of the preconditioning fluid is much lower than the bath temperature. When submerged in the bubble tank, the entrapped fluid vaporizes and escapes through the leak path. This outgassing of vapors creates a visible stream of bubbles. When used with low volumes in a well-controlled environment, this test method is quite accurate. However, the bubble test method relies on the operator to detect, identify, and reject the leaking device. This introduces the possibility of error to the technique, especially in high-volume applications and when testing devices with small cavities. In 1982, Webb began an R&D program to develop a more cost-effective gross leak test method, one that would consistently maintain accuracy in both high and low-volume applications, and be independent of cavity size. This R&D program produced the NID, vapor detection technique. Webb Technology has recently been awarded the exclusive U.S. patent for this remarkable innovation. With the vapor detection method, devices are preconditioned in a manner similar to the two-fluid bubble test. However, due to the improved sensitivity of the technique, preconditioning pressure times are cut in half. After removal from the preconditioning fluid, the packages are placed into a NID test cell heated to 125 degrees centigrade. This test cell provides good thermal contact to the device. As it is heated, the fluorocarbon trapped inside a defective part is vaporized and detected electronically by the NID analyzer. This flow diagram illustrates the process. Instead of depending on the operator to observe fluid leaking from the package, the NID uses an analyzer to detect the escaping vapor. The NID analyzer measures the concentration of fluorocarbon molecules within the system. If the measured quantity of molecules over a certain period of time exceeds a preset level, the part is rejected. In contrast to the bubble detection method, the NID repeatedly and reliably detects leakers without depending upon user judgment and subjectivity. The NID vapor detection method is a fast, accurate, and automatic means of detecting gross leaks in full compliance with MIL Standard 883, 750, and 202. Because of its suitability with today's high and low production environments, the NID method has become the preferred method for gross leak testing by manufacturers worldwide. By automatically identifying rejects, the NID eliminates user subjectivity, which in turn drastically reduces overkill and escapement. Overkill is rejecting a good device. Escapement is passing a gross leaker. With the bubble test, overkill can occur for many reasons. For instance, bubbles can be caused by fluid trapped in voids in the package material or the seal area. Bubbles can also be caused by residual flux or other harmless contaminants. None of these overkill examples represent true gross leakers. This is because with the bubble test, false leaks cannot be visually discriminated from true leaks, so they're rejected along with the true leakers. Like overkill, escapement is a costly result of user subjectivity. Escapement can occur if the operator doesn't pay full attention during the entire 30 to 60-second test. A device can emit either a short burst or a fine stream of bubbles, which could be easily overlooked, thus allowing a non-hermetic device to pass. Also, escapement can occur when the operator pulls the wrong device from the parts tray. As this field data indicates, the NID technique virtually eliminates both overkill and escapement. Webb provides NID correlation testing services free of charge. This testing can help to determine your overkill and escapement levels. In addition to increasing test accuracy, the NID offers numerous cost benefits over the bubble test method. Eliminations of expensive bubble tank indicator fluid, reduced preconditioning times, decreased handling damage, and increased yield all add up to significant cost savings. Payback periods of a year or less are very common. High volume testing is another NID advantage, either by testing large numbers of devices in a batch or by using as an automated handler to cycle devices through the test cell. If a group of devices is batch tested and the NID indicates a reject is present, the devices can be retested individually to locate the defective package. A second preconditioning step is not required per the MIL specs. Regardless of the model employed, the NID technique reduces operating costs and improves productivity. Webb can tailor a system to your exact requirements, taking into account the required throughput, desired degree of automation, cost, and other factors unique to your needs. Part 2. Webb Technology Gross Leak Test Product Line. Webb Technology is the only company in the world which supplies equipment for both the two-fluid bubble test and the NID vapor detection technique.